Today we're going to try to find the solution to an example using Ampere's law. We haven't worked with Ampere's law before, so let's start with the differential form of the equation. We have that the curl of the magnetic field B is equal to mu naught times the current J, the current per unit area. So this is the differential form of Ampere's law. But it's not very useful for when we're solving examples. Similar to Gauss's law, we'd like to use the integral form so that we can exploit some symmetries and work through some problems. What we want to do is we want to convert this to an integral form. So we start by taking the integral of both sides times the infinitesimal unit area vector. Where I can pull the mu naught immediately out of the integral because it's constant. And what this does is we have a vector in this curl times dA and the current J times dA. And this integral here, using what's called Stokes Theorem, we're actually able to convert it into a line integral. And that's in one step. We can go to the closed integral of the magnetic field times dl, which is the infinitesimal length vector, is equal to mu naught, again, times this J dot dA. And this step is what's called Stokes Theorem. One step further is looking at this integral here. What we have is the current dotted with the infinitesimal area vector. And essentially what we're going to end up with is what's called an Empyrean loop, which is going to be some surface, and we're going to have some current flowing. I'll call that J, and it will come out the other side of the surface. And what this Empyrean loop does is it works similar to a Gaussian surface in that whatever current passes through the Empyrean loop is what's going to be included in this integral here. And so what we can then simplify this to is that this is actually the current I that's enclosed by this Empyrean loop. And we end up with the final integral form of Ampere's law. The closed integral of B dot dl is equal to mu naught times I enclosed, where mu naught is the constant of the permeability of free space. Now that we found out what Ampere's law is in its integral form, we can use it to find the magnetic field outside of a straight wire. We'll do this by setting up a problem where we have a straight wire. We'll say it has current I flowing to my right, and it's a steady current. And we'll exploit what's called an Empyrean loop. And the Empyrean loop exploits the symmetry of the straight wire, and we're going to draw a circle centered on this straight wire with current I. And the reason we draw this loop is because we know that for magnetic fields, when the current is flowing to the right, because of the right-hand rule, we'll choose it such that my thumb points in the direction of the current and the magnetic field curls around that straight wire. What that means is at the top, our magnetic field will be pointing toward me out of the board, moving in this direction, so we'll say it's coming toward me. And on this side, underneath the wire, it will be curling into the board away from me. So the magnetic field will curl around the wire using the right-hand rule. And then we can use the Ampere's law in this closed integral form, which says that the magnetic field B, dotted with the infinitesimal length vector dl, is equal to mu naught times the enclosed current. And the enclosed current here is the current passing through this Empyrean loop. Let's say it's the Empyrean loop. Now, similar to Gauss's law problems with the electric field, we use this Empyrean loop to exploit the symmetry of the problem similar to the Gaussian surfaces that we choose in the electric field problems. So we always want to choose an Empyrean loop such that we know the enclosed current passing through that loop, and that's what this right-hand side of the equation is going to allow us to find. So now let's find the magnetic field outside of the straight wire. So we look at this equation and we know from the right-hand side that we want to find the enclosed charge by this Empyrean loop. Now this is straightforward in this case because the straight wire passes through the center of the Empyrean loop. So all of the current that's flowing along this wire will pierce this loop. And so I enclosed is simply I the steady current that's passing through the loop because all of the current passes through the loop. Complete the equation. Now we'll say that our Empyrean loop has radius s, and then by looking at the left-hand side of this equation, we see that we have a closed integral with a dot product between the magnetic field and the infinitesimal length vector. So we can start with that, saying that b dot dl, and we can find what this is equal to by remembering that the magnetic field curls around the straight wire, and so the magnetic field will travel parallel to this Empyrean loop at all points on the loop. So if I draw this loop, the magnetic field will be traveling essentially around in a circle along this loop. And this is important because while our magnetic field does that, our infinitesimal length vector will also travel around the loop in a circle, because at every single point on this loop, the infinitesimal length vector points perpendicular to the direction of the loop. And what that means is that b and dl are parallel at all points around the loop, and we can say that this dot product is simply the magnitude of b dotted with the magnitude of dl. And what that does is it allows our integral to become the magnitude of b dot dl is equal to mu naught times I. And we can go one step further, saying that this magnetic field has the same magnitude at all points on the Empyrean loop, and so we can pull it outside of the integral is equal to mu naught times I. And the last simplification step is that this integral is essentially the perimeter, or the integral around this Empyrean loop, which is just 2 pi times the radius of the loop, which is s, as we stated before. Now simply we just have to solve through for what the magnetic field is, and we say that the magnitude of the magnetic field is going to be mu naught over 2 pi s times the current I. And now it's challenging to figure out what the direction unit vector is for this magnetic field because of how it curls around the straight wire. But as long as we remember that the magnetic field curls around the wire and we put our thumb in the direction of the current, due to the right-hand rule, we'll know that the magnetic field curls around in this direction, out of the board toward me at the top, and into the board away from me at the bottom.